started. The recording is running, I believe. So I welcome you to session number 321 on automated design optimization frameworks. My name is Markus Zimmermann. I'm from the Technical University of Munich, and I am the head of the Laboratory for Product Development and Lightweight Design. So you can see our program for today. And before we get started, I would like to briefly present the authors to you. And so every author should please wave in the camera when I call his name. So in the first section, we will have Mr. Altun Osman from the Leibniz University. Then we will have Mr. Thomas Dickopf, who's still not here, but whom we will introduce as soon as he joins. We have Mr. Sanjay Nambiar from the Linköping University. We have Mr. James Gopsil from the University of Bristol. And finally, we have Mr. Albert Rosic from Flanders Make Institute from Belgium. So a warm welcome to the authors and a warm welcome to the audience. We will listen to pre-recorded videos now, all of them in one batch. And you have the opportunity to write questions into the chat, which we will use to for the discussion that will follow the video presentations. And please, if you state a question, I would ask you also to, in the beginning, to provide the presenter's name that this question is for. And I believe now we have Mr. Dickopf here. Mr. Dickopf, hello. Please, yes. Welcome to the session. You are from the company Contact Software. Welcome.
Right.
And now, Yelena, I guess we're ready. We're good to go with the videos.
Welcome to my presentation. My name is Osman. I'm a PhD student at the Institute for Product Development in Hanover by Professor Lachmayer, and I'm happy to be here and will present to you in the following minutes my contribution to the design conference. First of all, a few words about the research background and motivation. Generating new conceptual changes or variants for existing products in design engineering is very time and cost intensive. By applying generative design methods, we can reduce the development time, we can rapidly adapt to dynamic customer needs and fulfill mass customization requirements. Usually when we start to design manually, we often look at only a few variants and can miss the optimal solution by evaluating only a few. With the help of knowledge-based design methods, we can evaluate more variants in a semi-automated way through reasoning mechanisms. Coupling generative parametric models to numerical optimizers leads to a further solution space restriction, but offers the potential to alternate parameters as design variables in smaller steps and those to evaluate more variants and concepts. The main focus of this work lies on the GPDA, the Generative Parametric Design approach. We want to provide design engineers a framework to create automated design environments for functional assemblies. Now I want to introduce you to design environments according to the GPDA, which we described in our paper. A GPDA environment consists of a synthesis tool, which can be a numerical optimizer or a reasoning mechanism, an analysis tool, and a generative parametric geometry model, and of course the automatic exchange of property and parameter values between these different GPDA domains. Now let us take a closer look to each GPDA domain, starting by the geometrical domain. In this application example, we have a coffee machine, and based on its functional structure, we are dividing the product models into different design zones and relatively parameterizing them using a design skeleton. The parameters of the design zones are later used in optimization algorithms as design variables. Then we are starting to design the components, the structural components and functional components, and relatively parameterizing them according to the design zones. This means that when the zones are varied later in an optimization environment, the design elements vary automatically as well. Now let us take a closer look to the second domain of the GPDA environment, the analysis tool or the functional domain. For functional analysis, we are using MATLAB Simulink and formalizing the product variables, which are essential in relation to our objective functions and customer requirements and needs in the form of block simulation. By doing so, we can use the geometrical parameters and calculate variables, functional variables, such as how long does my brewing chamber need with the selected type of pump and heating element in my geometrical domain to, for example, serve 5 customers in 10 minutes. Therefore, we are using in each of these blocks several lookup tables, such as pump curves and so on, to be able to calculate these objective function values. Now let us take a closer look to the last domain, the optimization domain, or our synthesis tool. As an optimization algorithm, we are using the NSGA2 for multi-objective optimization problems, which is commonly used in design engineering problems. As objective functions, we choose the minimum working time and minimum water usage of our product, the coffee machine. And as design variables, we are using the parameters of the design zones and performance values of different design elements. Furthermore, we need to implement user scenarios to our functional domain, and we have used here user scenarios such as a hotel and an office environment, so we can calculate the objective functions based on these scenarios. Now on this slide, I want to show you the connection between the 3 different GPDA environments domains, the geometrical domain, the functional domain, and the optimization algorithm. The optimizer alternates our design variables, which are set as parameter values of our design zones and as values of discrete design elements, which are representing different solutions for functional components. By applying these values to our geometrical model, we are getting adjusted parameters of our design elements, such as structural components or functional components. By forwarding them to our functional domain, we can calculate in a block simulation the value of our objective function, such as minimum usage time and so on, and forward the value back to our optimization algorithm and reiterate the whole process until we are getting objective function values which are sufficient for our customer needs. The result of this whole process is a final geometrical model which is optimized for a given user scenario. Now on this slide I can show you a few examples of our optimization results. Here we can see the state of some parameters from the geometric domain on the Pareto front of our optimization. Each blue point represents a variant of our coffee machine, and the exact geometric dimensions can be taken directly from the CAD model itself. Furthermore, we can see that for different uses of functional components, clusters are formed, and those partial concepts can be excluded more easily, as we can see here on the right side. To wrap it all now up, here's a quick summary. With this work, we presented a first approach to build GPDA environments for functional assemblies to find the optimum of a product in early design stages. We divided our approach into 3 domains, a synthesis and an analysis domain, as well as the geometrical domain. And the coupling of these 3 domains is realized here by the usage of a numerical optimizer. And we have shown that different geometrical models results in different user scenarios. What needs to be addressed in future work? One question is how to identify optimal design zones. And the other one is how to handle moving parts, moving design elements between several design zones.
Welcome to my presentation on the topic Closed-Loop Engineering for Data-Driven Product Planning. My name is Dickopf and I'm Senior Research Manager at Contact Software. We are a tool vendor for PLM, IoT, and project management solution. Today, I will present you our results of the German research project Disrupt. Let's start with the current situation, the problems, and the challenges in product planning. Since only limited information and data about operational use is available in the early lifecycle stages of a product, product planning is typically based on hypotheses that are mostly determined and verified by market research methods. On the other hand, digitalization in the context of Industry 4.0 enables a wide range of data and usable information about a product and its use during its operation. So the question arises, why is this data not used to optimize the product during the product planning phase? Based on a study of the European Union on the right side of the slide, there are several obstacles to why data is not reused for further processes. Access denial, high costs, and interoperability are the main obstacles for European companies, to name some of them. So that leads to the following challenges. First, how can potentials generated from the operational product data value be reused? And second, how can companies, especially SMEs, be empowered, supported, and advised in the process of product optimization? These problems and challenges were the foundation of the research project Disrupt. The project is funded by the German Federal Ministry of Education and Research and is based on a consortium of industrial and academic partners from Germany. The main objectives of the project is to create a toolkit based on processes, methods, and IT tools for data-driven product planning. This toolkit should be validated by 4 pilot cases of different products of different industries. One major result of the project is the following closed-loop engineering approach. Concerning the obstacles shown in advance, this approach focuses on the interoperability between PLM and IoT systems, with the aim of ensuring data consistency and traceability along the product lifecycle. The approach itself is divided into 4 phases. In the first phase, the use cases of product investigation are defined by questions and hypotheses and linked to the product itself, an assembly, or a single part of the product. In the second phase, the digital twin of a product will be derived from the engineering data. Therefore, the bill of material will be classified in the context of which elements and sub-information are relevant in the usage phase of the product. Then, after synchronizing these information from the PLM system to the IoT system, the digital twin will be instantiated based on a generated template. The template itself includes product information from PLM as well as IoT-specific functionalities. In the third phase, the physical asset will be connected to the digital one, and the operation data will be managed in the IoT system. Then, based on the data of a single product or a group of similar ones, business applications and analysis can be executed, and product optimization findings can be derived. In the final phase, the findings are transferred back to the PLM system. Based on these information, the use cases for product investigation can be evaluated, and measures for product optimization can be derived and executed. In addition to the methodical procedure, this slide shows the underlying data model, containing the essential data objects of the PLM and IoT system, and their relations for interoperability in data-driven product planning. As you can see, these objects are also assigned to the 4 phases of the closed-loop engineering approach. In order to ensure industrial application, the approach was applied and validated by the products of the 4 pilot cases. In the following, you will see a screenshot of each phase of the prototypical implementation of the products of Weidmuller and Lasko. On this slide, you can see some insights from the application on the remote I/O system of the company Weidmuller. The little signs you can see show the process steps implemented in the PLM and IoT system. On my last slide of today, you can see how we use this concept to retrofit a hammer for solid forming and use that data to create added value for the product planning and development team at Glasgow. Thank you for your attention, and I'm excited to discuss with you about this and the other presentations in these sessions.
Good afternoon, everyone. My name is Sanjay Nambiar, and I'm a PhD student in Shopping University. This project, Autofix, Automated Design of Fixtures, mainly focuses on the field of design automation, optimization, and robotic simulations using CATIA, 3D Experience, and Mode Frontier softwares. This project has been made possible by Vinnova FFI, Autofix project, and Volvo Cars, Sweden. The goal of this project is to increase the degree of automation in the fixture design process. A high degree of automation is to be obtained by integrating design automation tools and MDO. Autofix is intended to be used as a tool which can automatically optimize the fixture design using knowledge-based engineering, multidisciplinary optimization, and machine learning in the future. This work is divided into 3 phases, focusing on design automation, robotic simulation, and design optimization. Some of the research questions developed during this project is that how can we access the flexibility of the fixture design, and how do this criteria help in increasing the efficiency of the production? And the last question was how can multidisciplinary optimization increase the flexibility of fixture design process? Well, the adaptability or reusability of the method with modularity in fixture design, along with the time taken for the entire process, is considered as a criteria to assess the flexibility of the design. And introducing reusable and modular fixture elements increases the reliability of the entire method by keeping stable quality in the product design, and low cost and high efficiency. With low cost and high efficiency, introducing MDO to the automation framework improves the model by optimizing it for reduced collisions between other fixtures and improving the ergonomic conditions for robot spot welding process. And this framework can be further developed to introduce cost, weight, and size of the fixtures depending on the customer requirements and specific VIW requirements. Body in white refers to the stage in automobile and manufacturing industry in which a car's component will be joined together using one of the combination of different techniques such as welding, riveting, clinching, bonding, etc. 6 body in white models having different fixturing or tooling configurations is obtained from Volvo, and the entire project of automation and optimization is carried out on these models. One of the important principles to consider while designing fixture is 321 principle. It states that a workpiece will be completely confined when banked against 3 points in one plane, that is P1, P2, and P3. 2 points, that is Q1 and Q2, in a plane perpendicular to the first one, and 1 point, which is R1 in the figure, in third plane perpendicular to both first and second plane. This principle ensures that all the degrees of freedom are constrained while fixturing a VIW model or any solid model. Design automation is achieved by using CATIA and VBA, as shown in the video. The fixtures are automatically instantiated at the must locating points specified by Volvo. All the fixtures and pickups are automated and parameterized using roles and reactions in CATIA. The shape of the clamps in the gripper unit is automatically changed depending upon the orientation of the sheets in the model. Once the automation is finished, this is how the results look like. As you all can see, the gripper units are oriented in 90 degrees, which can cause unwanted collisions. These collisions are eliminated using optimization in the next phase of this project. Once the automation is finished, the robotic simulation of spot welding process is automated in 3D Experience to extract the robot sweep volume during welding process. In this, the trajectory is automated from welding locations specified by Volvo, and spot welding operations are created at each of these locations or tags. Later, this process is simulated using teach operation and 3D Experience, and the corresponding STL model of the sweep volume is exported. The orientation of well guns relative to the well locations or tag is as shown in the left figure. The exported STL result is assembled on the automated model as shown on the top right. Since a small section of this volume is of our interest, that is the tip of the well gun, a dummy part similar to the area of interest in sweep volume is created and further used for the optimization process. Now comes the design optimization section, which is separated into 3 sections, that is objective formulation, framework creation, and Visual Basic programming. The objectives for this optimization process are clash-free assembly of gripper units and to minimize the volume of tooling components in the robot working envelope. Once the objectives were formulated, 3 inputs, that is the product ID of the gripper unit, the angle or the orientation, and the length of the clamp in the gripper unit. In this framework, the needler-made or downhill simplex method is used to find the minimum or maximum of an objective function in a multidimensional space. The framework is set to eliminate the clash in the model along with reduced intersection volume between the gripper unit and robot sweep volume. The angle and length of the gripper unit is changed in the CATIA by using parametric model for each iteration using VBA in the Excel node in the framework. Since we are using simplex algorithm, the best results will be among the last iterations. The orientation and length of gripper will be optimized one at a time as shown here. The graph shows the iterations versus clash of a gripper unit in the model. As we can see, there's a convergence after 7 iterations, and hence the value is taken as the final model. Here, it shows 2 clashes, which is between the platform and the BIW itself. So those are neglected and it cannot be minimized beyond that. It takes around 20 to 40 minutes to finish an optimization, depending upon the different BIW models. Once the optimization is finished, all the undesired clashes are removed and its comparison can be seen in the top right figure. When we look at the table, which shows volume and clash before and after optimization, we can see there are multiple clashes being shown in the results after optimization. At some clamping location, there are 2 sheets in contact with each other. Along with that, the collision with dummy volume is also taken into account. Hence, for some units, the best location will be with 4 clashes, that is 1 with the platform, 2 with the sheets or the BIW model, and 1 with the dummy volume. To conclude, the paper presents an approach for automation and optimization of fixture design process in the body and white industry. This allows the possibility of exploring the design space in fixture or tooling elements. Creating parametric models improve the geometric flexibility and increase the modularity of each element. The continuation of this project is going on with implementation of machine learning to predict the clamping locations and to calculate the ergonomic data using reinforcement learning and game engines. Thank you.
It's my presentation on Through-Lifecycle whole design optimization using software deployment toolchains. My name is James Gopsell and I am a Senior Research Fellow for the University of Bristol and Centre for Modelling and Simulation. In this presentation, I will discuss what we mean by Through-Life whole design optimization and the challenges in achieving it. I will then provide an overview of some of the software development toolchains and present our idea of how these could be used to overcome the challenges. I will then present an illustrative example and proof of concept of a design optimization that uses software deployment tools. This will be followed by a discussion of the opportunities and next steps in the research and leads to the conclusion of this presentation. So for design optimization, imagine you have a parameterized design space that you wish to evaluate. You'll want to generate each of the design options and evaluate them against your criteria. And we describe that as FFX, which will provide you information on whether the option is valid, and if so, how well it performs against the criteria. Design optimization is about finding the optimal and/or robust designs against our FFX. While simple enough, it becomes problematic when you unpack FFX. And in our case, we wish to evaluate our design against all manner of models that represent, the various different aspects of our designs. These models require different compute resources and runtime environments, feature different interfaces, require different knowledge and skills. And we want to do this throughout the design process as we create new models of high fidelity that we may wish to add to the optimization. So being able to evaluate our design option against all our models and being able to update the optimization as our models mature and new ones are created is what we describe as achieving through life whole design optimization. And in our paper, we reviewed design optimization literature over the past few years and developed 14 challenges in actually achieving this through life whole design optimization. So to overcome these challenges, we started to examine software deployment toolchains. One example of this is containerization through tools such as Docker. The process is to create an image that features all the dependencies for a piece of code to run. And in the figures on the right, we see we have images for a database, an API application, and web app interface. These are to instantiate and run a web application. And these, to instantiate those, we use tools such as Docker Compose or Kubernetes to ensure that software stack is run and operational. And if it fails, that those containers get reinitialized on the fly, so the end user sees no downtime. So for us, we thought, well, how could these tools be used to meet our challenges? And we began to develop a solution that uses these for design optimization. So what we came up with was a tool where we could select an optimization algorithm to use, such as grid, genetic, or swarm. And then that's then fed into what we are terming the controller code that accepts the design options that the algorithm wishes to evaluate. And the controller then acts as that intermediary, spinning up our containers that feature the models that we want to run. So it will run the different constraints and objectives that we might want to meet. And then those containers will output the results from those models, and the controller then digests those results and then puts those back into the algorithm for the algorithm then to come up with the different options. And reflecting on the challenges, we saw great potential for meeting all of them. Creating images of the models enables models to be version controlled, as well as avoiding conflicts with model dependencies. The controller creates containers with the right compute resources to run, as well as enabling hundreds of models to run simultaneously. So while that's all good in principle, we wanted to evidence this with a proof of concept. So we applied our approach to a simple constraint-based problem that you would typically find in a getting started tutorial. In our case, we wanted to find the XY point that lies below the red line while being above the blue line, and for the option to be as close as 0, 0 as possible. So we instantiated and created images for each of those different functions. So they were coded up in different coded languages for demonstration purposes. So one was in JavaScript, another one was written in Python, and the objective function was written in Golang. We would then use these containers of these models to run a refined grid search approach to find that solution in that design space. And here is the system in action. So what we have here is the Docker dashboard. As you can see, these containers are being spun up. Each of those is an individual model to evaluate part of a design option. That information is then being fed back into the controller and into the grid search algorithm to then update and evaluate new options to search for. And on the right there, we see the two figures of two iterations of the grid search. So in evidence, we've proven out that yes, we can use these software deployment toolchains to, image our models and run those simultaneously to evaluate design options. So now that the approach is, proven out, we can open up some interesting opportunities about how we can be efficient in how we run our design options. With some of the models, often taking longer than others, with this ability to have a controller in between our optimization algorithm and the running of the models, we could look at how we might, optimize to run them efficiently. So would we do a first pass on a subset of requirements of low fidelity models before committing to some high fidelity evaluation? All of those opportunities open up to us. And ultimately, we really want to come back to the stage by using such a process to do a whole design through life optimization of our design problem. Does taking this holistic approach fundamentally change how we design and ultimately the design that we create at the very end? So I'd like to thank you for listening, and our approach is available to download and use. So please feel free to go onto our GitHub page and have a look at it. We're really interested in looking for larger problems and more diverse design problems to really, trial this methodology out at scale. So yeah, thank you very much for listening, and I very much look forward to hearing your questions.
Good morning, good afternoon, and good evening. My name is Albin, and I'm going to present a new methodology to tackle the problem of optimal design when there are parameters that are uncertain, also known as robust design optimization. I will use an example during the presentation. The example consists of the design of a parallel electrical drivetrain. However, I want to stress that the methodology can also be applied to other cases. It's not specific for this case. So let's assume that a designer receives an assignment in which he or she has to determine the power of the two motors and the battery of the drivetrain, such that the total cost of ownership is minimized, and at the same time, some design specification needs to be fulfilled, like the vehicle needs to provide a given torque in standstill, needs to achieve a certain speed, and a travel distance needs also to be guaranteed. However, because this is an exercise to be made at the early stage of the design, some of the values of the parameters of the vehicle are still uncertain, not well known. So therefore, we assume that they will fall in a given range. Besides, we also assume that the engineer doesn't have a full understanding of all the equations used to compute the total cost of ownership or the specifications. Instead, there is a model available in the form of a black box model for which can be used to compute the performance of the resulting design. So therefore, we can put this model in what is well known as a model-based design optimization approach, in which the design parameters can be automatically and optimally determined by optimization solvers. So in that regard, there are different approaches to solve this problem. The first one is just not to consider uncertainty and fix the parameters to its nominal value. This is fast to compute. However, if the final values of the vehicle are not the same as the nominal, then we are at the risk that the design might not comply with the given specifications. A similar approach is also trying to prefix these parameters to what we think it's a worst case scenario. So that's very similar at the nominal design, but still we need to have these insights what the worst case is. In the case that we fail to provide the worst case, we are at the same situation as before, where some specifications might not be fulfilled. And a third approach is try to cover all the uncertain cases by fully sampling the uncertain parameters. So then we have higher guarantees that the specifications can be fulfilled. However, the computational times increase significantly. So here what we do is to propose a new methodology with the aim to fix certain parameters while also allowing that other parameters can be sampled. And the idea is to do this systematically and in a smart way. So what we do first is we perform sensitivity analysis on the design and uncertain space with the aim to gain knowledge on how these uncertain parameters affects the performance of the design. Once we have the results of the sensitivity analysis, we can, for instance, disregard or fix those uncertain parameters that has low sensitivity index, since they won't affect the performance. And also we can analyze the trends, and if we see that some of the let's say large values or small values of the uncertain parameter affects the performance significantly and independent on the rest of the parameters, we can also fix those parameters. So as a result, what we have is a combination of fixed and sample uncertain parameters that can be fed to the optimizer, and the problem can be solved faster while the design specifications can be fulfilled. So coming back to the example case of the parallel electrical drivetrain, here what we have is an example of the result of this sensitivity analysis, where we can see the different parameters and how they affect the TCO and the specifications. And after this analysis, we can fix certain parameters, while we also indicate that some of them need to be fully sampled. Then what we have in this table is the result of the different approaches. So first, we see that the nominal optimization it's compute quite fast. However, when we try to validate the design with a set of uncertain scenarios, we see that, for instance, the range for some of these scenarios are not fulfilled. So we were requesting 150 kilometers, and we see that the design only can provide 140. We have a similar scenario when we try to prefix the worst case. In that sense, it's the same computational time, but still here we fail to find the worst case. So as a result, when we validate the design, we still see that some uncertain scenarios doesn't fulfill the specifications. Then when we try to solve the problem by fully sampling all the uncertain parameters, here when we validate the result, we see that all specifications are fulfilled, so we cannot find a case that doesn't fulfill the specifications. However, the computational time is much larger. And finally, when we apply the new methodology, we see that all specifications are fulfilled, but the computational times are much closer to the nominal and the worst case case. So therefore showing the benefits of the proposal approach. So here I conclude my presentation, and I want to thank you for your attention.
So thank you very much for those very interesting presentations. I see that the chat is already well filled with questions, and I noticed that in particular the speakers had questions for each other, which I quite like, because this way we can perhaps, find the commonalities or the common theme among those presentations. I would suggest, I also have a couple of questions, but I would keep them for the end of the discussion. And I would suggest that we briefly go through these questions, and some of those were already answered, but I would ask you to repeat them, that the audience can profit from it. And so I would start with Mr. Gopsil. If you could just briefly repeat the question, and then also I would ask you posed this question to Mr. Altun, if you could answer it. Okay.
Absolutely, Markus. Thank you. Yes, a fascinating presentation, Altun. Yeah, I think you kind of also alluded to it at the end of the presentation about what's the largest change your optimization can accommodate. Because it felt like, yeah, you had to have the architecture defined. You couldn't physically move a component onto the other side of the design, for example. So I think you alluded to, actually, yeah, you want to have that optimization built up so it can accommodate different architectures. So maybe, yeah, if you could elaborate on how you might be looking to approach that, that'd be fantastic. Thank you.
Yeah, thank you for that great question. Actually, the design skeleton is already written down in the chat, has to be defined in terms of the orientation of the design zones. Within each design zones, we're placing my design elements and my functional components. There I have more degrees of freedom in placing them and orient them how I want. And also in sizing the design zones, I'm flexible. But regarding the orientation of the design zones, I'm at this stage not able to replace one design zone where I have such pumps and so on with another brewing design zone. Yeah, it will be a focus of the of future work, and yeah, maybe also a few words on the first slide where I said we are restricting the solution space to be able to put it into an optimization environment. We can actually extend the solution space again by adding just more design elements into my design libraries, which I'm then later alternating in my optimization environment. But yeah, the design skeleton has to be defined. That's right.
Actually, if I just may follow up on this, you mentioned that you can extend your solution space by adding more components. But adding components would not be part of your automatic procedure, I suppose, right?
It would be a part of it, actually. I defined such design elements called continuous design elements, where I'm just varying the size of a given design element, and I describe discrete design elements. These are design elements which I'm storing in design libraries, and I can put a lot of more such components in my library and alternate them as well. So within the design zone, I have a lot of freedom degrees. I can change components. For example, taking a heating element of a different type and just change it. But yeah, so just design zones are fixed and only changeable in the size.
Okay. So, Mr. Gobstill, I believe you had other questions. So I can't tell right now if your questions were answered. Should we move on to the next?
Yeah, absolutely. Yeah, that's fine. Yeah, that's it. Altun, yeah.
Okay. So, Mr. Altun, you have, I think, had the next question to Mr. Nambiar. Is that correct?
Yes.
Yeah, I actually really enjoyed your presentation with all those videos. It was nice to watch. I was just wondering regarding the mechanical analysis, if it's part of your work, or how do you plan to do it, the feasibility analysis of whether your structuring really is useful also in usage by load conditions.
Yeah, actually, that's one of our prime concerns while doing this project, actually, to include the stress and fatigue and the balancing of the BIW models in the framework and include that in the optimization framework. But that seemed a bit far too stretched for this project. So initially, in this work, the material, all the material details or material properties, it's preset. It's according to the company preferences, or it is more generic rather than we are not actually tweaking with it or playing around with it. So the physical properties of the materials or mechanical features, say stress, strain, the bending and the other features, it's not actually considered, although it is in vision to do it in future maybe.
Okay, happy to hear future works of you. Thank you.
Could you briefly, Mr. Nambiar, I remember from your optimization that you presented how those fixtures were moved around. Can you comment briefly on the objective function that you use? So what was the, let's say, the design objective of your automatic procedure? Was that only to avoid the clashes, or was there something else?
It is actually impossible to avoid the clashes in our framework. So what we kept as our objective is to minimize the clash volume between the working envelope of the spot welding robot and the fixture elements. So let's say we have an envelope of spot welding robot and we don't want any of the fixtures coming in the way or in the path of its spot welding. So we want it to be on the completely opposite side of it. So along with avoiding clash or minimizing clash, we kept another constraint to minimize this clash volume. So,
I understand. So, okay. Yeah. So considering all possible postures that would produce a clash. So, but it was purely geometrical then, your optimization, if I understand correctly.
Yes, it is purely geometrical. Yeah.
Okay. Okay, thank you very much. So then let's move on with the next question by Mr. Dickopf, addressed to, so I'm now getting confused. Mr. Gopsel is James, yes. So if you could briefly repeat your question and elaborate on it.
Absolutely, yes. Yes, Thomas. Again, I thought your presentation was really interesting, and I totally agree with this kind of iterative loop around, kind of deploying these design optimization frameworks and going towards industry 4.0 or digital transformation, whichever word you'd like to use for the day. Because that's what we're finding challenging with the organizations we work with, because it's such an investment that you need to do it over time. My one question on that is that once you've done one of those loops in your kind of infinity circle loop, did you have a standard approach to assessing the return on investment, so that an organization can start to see that value and then, okay, we'll do this loop again, and we'll keep doing that loop, and how they assess basically how successful it has been? I think we've got an issue with your mic.
Dickopf, oh yes, no, I think now we can hear you. Now, are you speaking? There's some kind of an...
Okay, in case of video or audio problems, I suggest to try to refresh the page.
Okay. But that would that was meant for Mr. Dickopf, I believe, right?
Yes.
Okay, Mr. Dickopf, so I guess we will lose you for a couple of seconds. In that case, I would move on, and I would ask Mr. Rosik to ask his question to at Mr. Nambiar.
Yes, well, first to thank Mr. Nambiar for the presentation. I also agree with Altun. It's a very nice presentation. I was wondering if I understood well, there are a set of choices that are sequentially done, like, for instance, position and orientation of the fixtures. If this is right, I was wondering how this sequential sequence affects to the optimal result. So how, because you fix one to the other, how it compromise the optimality of the result compared to optimizing all at once. And also, I wonder if this has been analyzed, or you can at least give some insights on this.
Actually, yes, we have analyzed optimizing all at once. That would logically save us a lot of time comparatively than optimizing one fixture at a time, or one clamping unit at a time. But the problem is when we optimize all at a time, there are some situations or some cases where we want one particular fixture to be oriented in separate way, and then the next fixture can be optimized according to the previous one. So the positions of some grippers are like interdependent on each other. So we had to take that into consideration. So what we did is, in order to avoid all changing simultaneously, we created a loop such that it will take one at a time, and it will create a pattern. Let's say we have like 10 fixtures, it will optimize 10 fixtures one at a time. And if the optimization is done, and we'll change the loop pattern, we'll randomize these 10 fixtures, the orientation, it is optimized for the next iteration. Let's say in first iteration, we are going 1, 2, 3. In second iteration, it might go 5, 6, 7, or in a different way, so that we get different orientation. And we are taking the best design from that according to the simplex algorithm that we taken. Like you mentioned, we tried that first method, but the time taken was huge. Not huge, I would say, comparative to the end result. It was not worth it, because we were sitting on it for like hours and hours, and without any good results. So there is that. And regarding the selection of points, it was done in a sequential way. And in this project, we are taking, I think James Gospel have had another question regarding the designer's position in the design space, how he stands in this process. Well, for this project, the designer has given us a couple of suggestions where the point should be, where the clamping location should be. So he has already given that. And out of, let's say, 10 position, he's picking, or he or she is picking 1 or 2 according to the needs. And that keeps changing according to the designer's objective. When he finds out, okay, this can't work, he'll go for next point, something like that. So in this case, we have prefixed certain points and we are automating on them. But the next process of this project, of this Autofix project, is to automatically detect these 10 points or the points described by the designers and completely take out their decision by using machine learning and supervised learning in this. So we can actually detect the clamping locations automatically. And then this part of the project comes in by automating and optimization of those particular points and those particular clamping locations.
Yeah, things clear enough. And
did I mess it up, or I hope?
No, it was clear.
Yeah. Okay.
Yeah, and thank you for also kind of leading on to my question there. I believe we've lost Markus, our chair, so I'll just jump in. Hopefully, you'll come join. So that's what exactly. It's interesting that you've mentioned how you used the designer to actually seed the design space, the optimization, rather than just using, a random seed. Just randomly place it and doing the optimization from that. So, yeah, in use of using a designer to seed the exploration, to have them in that loop. Yeah, like I said, we've had experiences where just leave it for an optimization to provide it. The designers are still unsure and not confident, so being in a loop may give them that confidence and trust in what the process is doing, and ultimately they are yes.
James, I don't know if it's just me. I think there's a lag in your voice. Oh, I couldn't hear the last part of what you said. I don't know if it's just me.
The same on my side.
Yeah. Oh, sorry, chaps. For the design key, key element. No, gonna have to refresh then. Issues in the session. I think Markus is back. No, I forgot. Having issues.
We can't hear you, Markus. We can't hear you.
Can't hear you.
Can you hear me now? Oh, perfect. So I think it was a Firefox problem on my side.
I think Markus is talking, but apparently we can't hear anything from your side.
I can hear him actually.
Really?
I'll have to refresh.
Oh,
we're losing.
no, everyone is rejoining again.
Yeah, he left now.
I see. Jelini, you can hear me. Is that okay? Yeah.
Yes, now it's okay.
Okay, I'm good. That's it. You never know who it is.
Yeah, I can hear you, James.
Awesome.
Just not Markus anymore.
No, his video is good. It looks like the mic's not connected. Because I can't see the... Yeah, because the video is coming through good.
Yeah, we can actually proceed. Which questions are left in the chat?
Markus, we cannot hear you.
I
suggest you to
Thomas.
switch to Google Chrome.
Again?
Okay, yeah, we can try to. So I had a quick one then for Albert. About, you talk about the time savings, and there is this considerable considerable time savings for your new method. I was just wondering if that was all about also maintaining the same compute that was available, i.e. number of CPU cores and graphics. So it's all on the same platform. It was all. Is that right in saying?
Yeah, I can elaborate. Yeah, so actually, for all the different approaches that we test, we were running in a dedicated computer. Only this simulation, so it's the same CPU, the same computational power. Even to guarantee, because that's not the proper way to test a complexity of the algorithms. We know this, but probably the easiest way to do it.
Mm-hmm.
We also had to run the optimization several times in order to guarantee that they were not falling in local optimals. And then we're doing the same optimizations with different initial starts.
Mm-hmm.
And then we also verify that the same optimal or pseudo optimal was found every time. So, and also at the same time we saw that the same computational times were applicable. So in that sense we are quite sure about the gains in time.
Mm-hmm.
But maybe also to give more information. So we also detected, and I didn't mention this in the presentation, that the method that we propose, it's quite easily can be easily parallelized. Because you can you sample the parameters, so you can run the different samples on parallel and then try to combine the results out of it. So then even the gains are bigger there.
Mm-hmm. Yeah, because same with our collaborators and project partners. They want to use these optimization algorithms more and more. Of course, ultimately, then that's a lot more compute resource they're using, and reflecting on sustainability and carbon footprint. They're wary of, using, like you said, nicely highly optimizers, as it were, that are run efficiently. So you're not just burning CPU and GPU, energy. It's interesting to see that. And also, I guess, how often would they like to run this optimization? Then the problem that you propose, do they typically do that on a weekly, monthly, daily basis? Is that where they wish to go to?
Yeah, the approach that I presented is meant for the early stage of the design.
Mm-hmm.
I wouldn't say not even to find the final values, but to help the designers or the people who are in charge of the design to take the right decisions, to make sure that early decisions are done in the design phase are not going to compromise later on the real performance that needs to be fulfilled there. So in that sense, the idea is that you run this optimization a few times at the beginning. It might take time, so it's not something that you want to solve maybe in a few minutes or seconds. So you can allow it for several days even. But what we don't see is that the optimization needs to it's more than weeks. The solution that's probably it's not something that you want to test and retry and redefine.
Absolutely, I can imagine that's in that conceptual design phase where it's really creative. You want to be able to iterate so quickly. So that time saving helps people maybe maintain their mental model of what's going on, so they can iterate more. So absolutely. Markus is back. Hopefully, let's see.
So let's try.
Yes.
Can you hear me?
Yeah.
Yes.
Now it works. Okay. Well, it's a different browser. It's not Google Chrome, but I think you probably made progress without me. So I wonder if you really need me. Have you gone through the questions from the chat? Because I unfortunately I lost my chat.
Yes. I think we've covered all the questions in the chat. Unfortunately, Thomas has been unable to reconnect, but yes, he's already sent something in chat to be able to email him, and okay. I'm sure use the chat in Hopin.
Are there? Please, from the audience, write down your questions if you have any. And meanwhile, I guess I would pose a question to all speakers if you feel able, or if you'd like to provide an answer to that would be nice. So for me, there are typical problems associated with design optimization, and one of these problems we started discussing when Osman Altun, when I asked you about what happens when you add a component, and you said, well, you have discrete design variables that you can use to switch on and off components, I believe. Well, but what do you do when you have associated with those components extra design variables, extra degrees of freedom that you would have to address in your automated process, or on top of that, even dependencies with other design variables that you switch on and off? Is there an idea, or do you think, can you think of approaches how to deal with this? I'd like to call this operating on unstructured design spaces. That's a term that I'm not sure if it's commonly used, but I saw some nodding, so I guess you know what I mean. Do you have any ideas on this?
Yeah, I'm happy. Yeah, Altun, go for it.
Okay. Actually, on my approach, we are giving each component or each function a design variable, and I can exchange the requirement fulfillment or the function with different components. So I don't have the problem to deactivate the design variable or activate it again. The function has to be fulfilled, and I can do it by changing the component to fulfill the function. But on the other way, to have a more generative optimization environment, I guess we need to work also on how we can disable a design variable, and based on that also having a more generative functional simulation, where I can also generate, based on the number of my design variables, the calculation of the objective functions. It's really a challenge which should be addressed in future work as well. But in that example which I showed, there was no need to disable or enable a design variable.
Okay.
Fantastic. For myself, Markus, that is a perfect phrasing to actually what we are looking to solve, operating in unstructured design spaces. And the idea of being able to containerize your models. So, like you say, I presented a very simple, set of functions just written in Python, Go, and JavaScript. But you can imagine if that's just your initial concept design, where it is just a function normally, just to say, hey, this is how pressure changes with diameter. But then later you might want to say, okay, I'll replace that with an FEA simulation with a CAD model. And of course, you just take that container out, you plug the other container in. The only thing we need to update is in the controller, which are the parameters it can vary and give it the ranges. So again, maybe in a concept phase, it was just a parameter P. And then by the time you get to FEA, that's then split out into 10 different parameters that you could vary. You just change that into the controller, and then that goes into the design, the algorithm, and off it goes again. We're really excited to see how you could evolve, that design options. So you're just plugging in and out these containers as your models get refined and more detailed, and seeing how that design space evolves over time. I think that's going to be a really exciting space. Where it went across the time.
Very good. And any other comments? So, Mr. Nambiar, if you wanted to add another clamp, I guess, could you do that in your framework?
Yes, I can.
Good. Short question, short answer. Very good.
We just have to specify in the user interface that I didn't show in the presentation. We have an Excel user interface. You just have to specify either the point coordinates or if there is already a point built, we just have to specify the name of the point.
Okay.
Maybe a related question. Can you also optimize the number of clamps, or this is not considered?
Actually, the optimization frameworks depends upon the number of clamps present. So if you add...
that's what I actually meant to ask, really. So I think I didn't pose my question precisely. What I wanted to ask is, can you optimize with respect to the number of clamps? Yes, exactly.
Exactly.
That's
So as soon as we start the optimization, the initial section is to gather the information regarding how many fixtures are there or how many gripper units are there in the model. So if we change the number of models before we start the optimization always runs according to the number of units present in the model.
Mm-hmm.
Yes.
Okay.
I think that answers your question, Albin.
Okay, thank you.
Yes.
So, if there's no other question from the audience, I would ask another, like, let's say, very general question related to automation of design. Well, I see design automation from a, let's say, numerical optimization perspective, and whenever you use numerical optimization, you have a very strong, a very formalized setting. You have your design variables, you have your objective function, you have your constraints, and so in some sense, it suggests that for any automated process for design, you also need a very clear description of your goal. So you need a very formalized definition of where you want to go, and very often you don't have that. So do you have any ideas and insights on how to deal with this, let's say, kind of a fuzzy front end? I mean, will optimization or will automation eventually fail when you do not have crystal clear goal definitions? Do you have any ideas on that?
If I may, can you hear me? So I've lost
Yes.
a few images. Good. So we've done a bit of work using, I say, machine learning and AI to try and capture human perceptions. Let's say, one aspect we've done is look at, let's say, images of, say, the front end of a car, to say if it's an Audi or a Volkswagen or BMW, by taking those and then using machine learning to try and pick out the salient features that they go, if a user looks at it and goes, yep, that would be an Audi. So you feed that into the optimizer. So the machine learning algorithm, the AI, as it were, is trying to mimic what the population might perceive a vehicle or a form as. So that's a way of what we're trying to do, almost numerically, computing what human perception is. So we've used bits like that. We've dabbled in, I don't know if you've ever heard of AWS Mechanical Turk, Amazon Web Services Mechanical Turk. It's a way of getting mass user data back on, so effectively like sending out a form to lots of people, and you can pay people to fill out a survey or form. And we've played with that idea, the optimizer producing designs, then people saying, yes, I like it, on a kind of Likert scale feedback loop. Of course, then you're making it a numeric number, and then that gets into the design. So you are adding that kind of human in the loop into the optimization algorithm. So I think there are a few techniques out there to try and objectify the subjective, as it were.
Mm-hmm. Any other comments?
Yeah, for us, what you mentioned, it's quite similar what we try to do with multi-objective optimization. So maybe there are clear goals, but they are a bit conflicting each other. And what we experience that sometimes it's difficult to formulate this multi-objective in a consistent way that it provides the right solution. And what we try to do is, instead of trying to find that optimal design, is to provide to the end user a set of potential good designs in the form of Pareto form or in other forms, so that he's better positioned to make the right choice. So it's not the optimal design, but it's a kind of a filter where you can present the good designs and you can scrap out the things that are really not relevant for him or for her, and then try to make the right choices. Things that we see often, for instance, is when it's cost performance, there are clear conflicts there, trade-off to be done. And sometimes it's not clear. If you have to find what is the right trade-off, it's better if you can present the two ends and whatever happens in between, that they can make the right choice. So that's what we try to propose, and I think it's quite similar what James was saying.
Up to how many output? How many outputs have you applied this Pareto optimization to? So you showed your what is it called again? The NDG, the optimization algorithms to compute a Pareto front. Have you applied that to more than two quantities of interest, or more than two objective functions?
Yeah, so a bit it is that you can, so that the objective function needs to be can be multiple, so even more than 2, 3, 4. What we usually ask, for instance, is to define how many designs you want to get as an answer, and then we
I
try
understand,
to
but how many objective functions have you applied it to yet?
So usually,
because you can in 2 dimensions, you can show the Pareto front very nicely.
Yeah,
and then you can talk about non-dominated design. That's very beautiful. But have you tried it to 25-dimensional output?
No,
yet?
it's not for this case, but we apply for a 3-dimensional, and then you already run in programs when you want to visualize things. But then, you need to use, and also was part of another project where we apply a visualization techniques where you just can select in one plot one of the promising design and see how it reflects to the other objective to see what that design falls in the other objective. In theory, you can do this for 25 dimensions. That's probably it's not desirable. And another thing is also to filter the information that is relevant for the user. So if there are goals that are not clear or they are not relevant for him, I think that then shouldn't be there. I see often in design problems that all the information is put into optimizer, but sometimes not all the information is needed to find the optimal one. I think that techniques that can reduce the problem, the initial problem, are also welcome there. You can have 10 objectives, but maybe not all 10 are relevant for the design.
Okay. Any other comments? Okay, so I guess there are still no questions from the audience then, but I think there were many questions discussed already. Since we're approaching the end, I would like to thank the speakers, and unfortunately we cannot applaud, and even more unfortunate is the fact that we cannot sit at the beaches of Dubrovnik this evening. So thanks for presenting your interesting research online. I'm going to close the session now, and hope we stay in touch and see you in 2 years in Dubrovnik. Thank you. Bye-bye.
Thank you very much, Markus. Thank you, everyone. Cheers.
Bye-bye.